Hello everyone. This is part 3 from our series Mathematical Image of Infinity in Dividing Geometrical Shapes. In this video here, I'm mainly focusing on multi-dimensionals, more than 2 or 3. And then we try to generalize the theorem in which we introduced it in the previous 2 videos. Let us just call back my previous works, and then the first one was on two-dimensional. Then simply here, if you have got any regular two-dimensional closed loop, this can easily be converted into a circle with radius r, and then the same area as the area of this irregular shape. There are two notations in which we introduce to simplify our explanation. One of them is called omega 2 and one is omega 1. In this context, omega 2 simply means the area, but obviously here once you increase the dimension, these omegas meaning will change. And omega 1 is simply related to the perimeter of the shape, or in the case of circle is the circumference. And simply here, if you have got any coordinate system psi 1 and psi 2, obviously omega 2 is this double integration. This is a function in which exists within here or here, and then certainly here omega 1 is the length or representing the length of this perimeter, or in the case of circle, the circumference, and both are normalized. This is more general. For example, here now, if you have got a circle, and then if you divide it into n smaller circles, given that the total area is equal to the area of the original circle, then you come to a conclusion that the total sum of these circumferences is equal to 2 to power n divided by 2 in ratio to the original one, in ratio. And then this new notation here, this is omega 1. Omega 1 means the one-dimensional, which is the perimeter or the circumference, and then n reference to the number of divisions, which is equal to 2 to power n divided by 2. And then certainly here we showed it that if n approaches infinite, this sum will become infinity. Then we extended it to 3 dimensions, which is fairly easy. If I have got any 3-dimensional, and then this can easily be converted into a sphere of radius r with the same volume. And don't forget, always this sigma or omega 3 can be kept the same in both. But omega 2 does not have to be the same, or may not be even the same. The triple integration for omega 3 after normalization can be written in the following way, and then double integration representing the surface area of this shape, or in this case in our sphere, it can be given, for example, in double integration the same way. Psi 1, psi 2, psi 3 are any coordinate system, can be Cartesian, can be polar, can be spherical, and then whatever. For instance, here now, if you divide this sphere here into n number of smaller spheres, and then in this case, the ratio of the surface area of the sum of those to the original is equal to 2 to power n divided by 3. And then in the new notation, because the surface here represents sigma 2 and n is the number of division, which is 2 to power n divided by 3. So do not forget those two are exactly the same, but for a reason we introduce that, in which you will see it shortly. In the case of 4-dimensional and higher, briefly here, why in general we introduce many dimensions? For instance, here, if you look at mathematics here, usually whenever we introduce these dimensions to explain or to understand some other phenomena in which maybe not explained easily within normal context, and then having more dimensions can simplify or can explain like a model. In algebra, many dimensions normally are constructed in abstract form. Then even they may not have any physical or geometrical meaning for the purpose of independent variables. In geometry, we would like to have some geometrical meaning, but unfortunately here if the dimension exceeds 3, this may not be easy. The situation in physics may be different. You have got, for example, now 4 dimension, which is time. Perhaps visualizing it in geometry may not be easy, and then according to new theories, so physicists may assume that even universe or maybe particle physics, there are 10 dimensions and each dimension may represent something. Visualizing those geometrically may not be easy, but introduction of those dimensions are just for the purpose of setting a model to explain some phenomena in which maybe we cannot understand it in a normal sense. Although the purpose of this video is not touching those dimensions in detail, but there is one element we need to know. If, for example, we have got a situation or maybe an object here has got m dimensions, obviously sigma m minus 1, like the case in which we had for 2 or 3, will exist or can exist, for example, in omega m, or maybe you can say this is a subset of that. For instance, here like the sigma or omega 2, and this omega 2 here of a closed 3D shape is part of or exists in omega 3. Omega m can be given by this formula for any shape, or omega m minus 1 can be given by this formula. You do not need to worry about the complexity of this formula. Psi 1, psi 2, psi 3 to psi m will be the coordinate system. Then it doesn't matter which type of coordinate system we use, but there is one important point here in which we need to know. Any of those shapes we have, normally in more than 3 or 4 dimensions, we can call it hyper objects here, because we cannot visualize it in the sense of a normal geometrical shape, but we can set up a model here to represent that this can be converted to a hypercircle or maybe hypersphere or hyper object here in which it has hyper radius. And then certainly in the analogy of the previous one, omega m can be proportional or is proportional to r to power m, and omega m minus 1 is proportional to r to power m minus 1, according to the same conclusion. And then the previous results can be generalized in the following way. For example, here, if you have got an object in which it has m dimensions and you divide it into n smaller objects, then the ratio of the omega m minus 1 at n is equal to 2 to power n divided by m. But there is a very interesting result. If, for example, you have got a universe in which it has got infinite number of dimensions, so you notice that this becomes 1. In contrast to the previous cases, if you can remember, when the number of dimensions are limited, then this approach infinite, but in this case, it is approaching 1. So it means the total sum will be equal to the original figure in which you have for omega m minus 1. But this is a simple graphical illustration here for the previous result. You have got an axis, this is the number of dimensions, For example, here 2, 3, 4, and then even it can go for wherever you want. And this is ratio of the sum of the individual manifolds to the original, which is omega m minus 1. And in that direction, this is the number of division. For example, this yellow graph has got more division rather than this red or rather than this blue one. But there is one interesting point here. When the number of dimensions increases, all will merge to the same. So it means all will become one. Hoping you have enjoyed this video, and then I will see you in the next video. Thanks for watching.